Hi everybody, I'm going to share with you our work titled Optimization of Circumferential Temperature Uniformity of a Parabolic Trough Collector Absorber with U-Pipe Exchanger. This presentation will focus mainly on the following axes, starting by the problematic of this study, the purpose of this work, some description of simulated prototype, an optical and thermal analysis of the system, and we are going to present some results, and the final axis is a conclusion. The study and the investigation of the flux and temperature distribution around the absorber remain very important, not only to determine the temperature gradient existing at the absorber area and consequently to avoid material damage, but also to optimize the operation and reduce the optical and thermal losses around the parabolic trough collector receivers. The aim of this study is to realize a numerical investigation of a parabolic trough collector with U-pipe exchanger, analyze the flux and the temperature distribution on the absorber circumferential, and finally to evaluate the effects of the flux uniformity and temperature distribution on the system efficiency. This table presents the technical specification of the prototype. The simulated parabolic trough collector prototype is consistent of a 2 square meter reflector area, 12.5 geometrical concentration coefficient. This figure presents a photographic view of the prototype, and this second presents an illustration of a developed view of solar flux in the absorber circumferential. The optical analysis were carried out under an optical simulation software SolTrace. This figure presents a circumferential distribution of the flux for different focal distances. According to this figure, we can observe clearly that the flux distribution on the outer surface is symmetrical, and the focal distances have a significant effect on the variation of the flux distribution. However, we can notice that the highest local concentration ratio is achieved for the distance of 0.90 meter. The thermal simulation is realized under ANSYS software. The heat flux profile of circumferential distribution is exported from the SolTrace simulator. The working fluid in this study are chosen as water. However, all thermal properties of material constrictions and fluids domains are taken from the ANSYS library. Then the flux circumferential profile is considered as a boundary condition of the absorber tube outer area. The figure here presents the structural model of the parabolic trough absorber component in the CFD analysis. The area on the absorber tube is discretized on 36 surfaces, and the second figure here presents the mesh generation of parabolic trough collector absorber component in the CFD analysis. As a result of this study, we can see clearly the temperature distribution on the absorber tube for all distances. The maximum temperature distribution over the circumferences of the absorber always appears around the part where the outlet liquid is located for all distances. So the maximum circumferential temperature on the absorber tube is about 315 Kelvin reached for the distance of 0.90. This last figure presents the variation of thermal efficiency and temperature differences on the absorber wall in 3 positions for different focal distances. The thermal efficiency evolve with the focal distances variation of the absorber tube. The presented results reveal that the thermal efficiency for the all cases are between 7 and 45%. The higher thermal efficiency among the focal distances is reported for the distance of 0.90 meter, which is about 45%. Based on the thermal efficiency comparison and temperature differences between different parts of the receiver, the studies were carried out for 5 focal distances. The system reaches a maximum thermal efficiency of about 45.3 in the case of the distance of 0.90 meter, which is higher compared to other distances. From this investigation study, it was concluded that solar flux and temperature distribution optimization remains a crucial solution to design and resolve the absorber tube problems. Thank you for your attention.